Shall we start?
I'm ready. So, well, thanks, Samara and Jim, for setting this all up and inviting me to give a talk here. I'm going to tell you guys about, this is the only time I'm going to use this board. I'm going to use the iPad, of course. I'm going to tell you about this, this work in progress with Vitaly Brejevs, who's, I think, also here. And we're looking at the chi-sliceness of three braid links. I'm going to define what all these things are, what chi-slice means and everything. But the first thing I want to do is give a little background and why I'm personally interested in this story. And so let me share my iPad now. Move over to here. Okay. Actually, let me rotate, make it bigger for you guys. Okay. So I'm just going to start with some basic facts, or one basic fact that interests me. It's if you take a knot in the three sphere, and it happens to be a slice knot. And so slice means that it bounds a disk in the four ball. So the knot bounds a disk in the four ball. And in the story, everything I'm going to be dealing is smooth. So all the surfaces I'll be talking about knots, it's all smooth, although I'll never explicitly say it. So if I take a knot and it's sliced, then if you take the double cover branched over the knot, that should be a K, not an L. Not ready for links yet. So this is the notation for the double cover of S3 branched over K. When I do that, whenever I have a knot, this is automatically going to be a rational homology three sphere, and it will bound a rational homology four ball. This is like a well-known fact in low-dimensional topology. And so a rational homology four ball, what is that? Well, it's a four manifold that has the same rational homology as the four ball. Another way to say it, if you look at the regular homology with integer coefficients, all the homology groups are torsion except like the 0 with 1. And so this is just a classic fact. Double branch cover over a slice knot gives you a rational sphere bounding a rational ball. So I should say that too. This is automatically a rational homology three sphere. If it wasn't a rational homology three sphere, it wouldn't bound a rational ball. So it only makes sense to bound a rational ball if you're a rational sphere. And this is a pretty nice construction. A lot of folks are interested in classifying families of rational spheres that bound rational balls, and this gives you a way to construct them. And that's kind of the angle I took when approaching this project and what interests me in one of the reasons why I'm interested in knot theory. Maggie gave a lot of reasons why knot theory is important to study three manifolds or four manifolds, and here's sort of another thing. She sort of talked a little bit about branch covers, and this is sort of the perspective I'll be taking. So the question to explore, one might ask here, is like, this is if you deal with a knot, but what if you are dealing with links? Is there something you could say similar for links? So do links have or are there links? Let me say, what kinds of links have similar properties? Meaning, if I take a double branch cover over a link, can I bound a rational ball? If so, what do those links look like? And so that's what I want to think about. And there's a lot known about this. And going back to Casson and Harrer, so the first result here goes back to Casson and Harrer. This is from like the 70s, maybe even like 72, early 70s. Also Liska, this was in, I don't know, the 2000s. And they proved the following thing. If you deal with the link, if you have a link, L is a link, with determinant non-zero. So before moving on, I want to say a quick word about this condition. Having non-zero determinant ensures that the double branch cover is a rational sphere. If the determinant is 0, then it's not a rational sphere. So it wouldn't make sense to bound a rational ball anyway. So this is not really that restrictive of a condition or anything. This is just to ensure that bounding a rational ball is even possible. So this ensures that the double branch cover over this link is a rational sphere. So if I have a link and double branch cover is a rational sphere, and it bounds a certain kind of surface. This is going to be a properly embedded surface. Ooh, I missed a key word here. Ribbon surface. With no closed components and Euler characteristic 1. Then the double branch cover of S3 over L bounds a rational ball. And that rational ball that you can show is, I mean, there could be a lot of rational balls, but one in particular is the double cover of the 4 ball branched over the surface. So, sorry, I guess I didn't call this surface anything or tell you where it lives. So the surface is F and it's in the 4 ball. And this is also the case for slice knots. This is actually, you could think of this as being contained in here if you're talking about ribbon disks, sort of a special case of this statement. And so Casson and Harrer, the proof that they give a little bit of history here. I'm not going to spell out the proofs, but I'll tell you the quick idea. Casson and Harrer, they focused on the idea where L was just, or the surface, L was a 2-component link and the surface was a disjoint union of a disk and a Mobius band. So that was the Casson and Harrer case. F was the disjoint union of a disk and a Mobius band. And they proved this just rather geometrically. Whereas the Liska proof does this proof in generality. It's for any kind of surface of Euler characteristic 1. And this really just uses homology arguments. I'm going to move this down a little bit because I'm going to add some explanation stuff above. So the one thing I want to mention is this word here. So this ribbon surface idea, and this is sort of going back to some pictures that Maggie was drawing, which I'm going to be drawing as well. So what do I mean by a ribbon surface? This means, if you think about, Maggie was drawing these pictures of like height functions and everything, so we could think about it in that way. But I'm going to think about this function as like the radial distance function. I'm going to put a function on the 4 ball, and I'm just going to be measuring the distance from the origin. So with respect to the radial distance function on the 4 ball, the surface F has no index 2 critical points. In other words, there are no maxima. Or if you're thinking about handle decompositions, there are no 2 handles for this surface. So you can think of this surface as being built out of disks and then just 1 handle that you're attaching. You don't have any maxima. So that's what I mean by ribbon. And so in this case, this geometric argument, it was kind of crucial that it was a ribbon thing. And really what they did is they took the 4 ball and they put the surface in a really convenient position, kind of like the way Maggie explained, where you push the index 0 critical points, those disks, below a certain level. And then in another level, you have all of your 1 handles, your index 1 critical points. And they just looked at what the double branch covers are over each of those pieces and then glued them together and showed that you ended up getting a rational ball in the end. Whereas the Liska arguments, which is better because it works for more general kinds of surfaces, it's just homology, and you just look at essentially the long deck sequence of the pair along with Euler characteristic calculations, and you're able to prove it. Now there's one key ingredient here that was absolutely necessary. I did not spell that right. Key ingredient. And that is that the Euler characteristic of the surface is 1. If the Euler characteristic of the surface is not 1, then this double branch cover will not be a rational ball. It'll be something different. Now that's not to say that the double branch cover over the length does not bound a rational ball. It just says that this one is not a rational ball. So it could still bound one. But this is a very key ingredient for this proof that you cannot remove. You cannot change this. A not so key ingredient is the ribbonness of the surface. So the fact that it's ribbon, that makes the homology argument somewhat simple. And all you have to do is look at the long exact sequence of the pair. And because the surface is ribbon, you can argue that this double branch cover, this 4-manifold, has no 3 handles, or admits a handle decomposition without 3 handles. So it's pretty easy to work through. But if it's not a ribbon surface, then this rational ball could be more complicated, this double branch cover. So there's more going on. But you can upgrade this and you can remove that ribbon condition. And that's the content of the next theorem. So it's the same exact statement, except I just removed ribbon from this. Everything else is the same. I have a link, non-zero determinant. I bound this surface with Euler characteristic 1 in the 4-ball. You take the double branch cover over that surface, you get a rational ball. And the proof of it, it's also just homology arguments, but it's a lot more involved. You have to bring in other kinds of long exact sequences to prove it. So just more homology. I'm not going to say anything else about that though. And so this theorem was due to Donald and Owens in a paper from maybe less than 10 years ago. And so this theorem, I mean, it certainly answers.
Jonathan, this is BG. I have a question about the Donald Owens theorem. So it's not constructive? So this rational homology for a ball?
No, yeah, it's all just homology argument. So you're doing the double branch cover, so it's constructive in that way. This is the rational homology 4-ball.
Oh, I'm sorry. Okay, sorry. Yeah. Okay. Thanks.
But you don't like sort of see what it is. You don't end up with like a nice handle description of it. Like for the Katz and Harrer argument, they sort of had a nice geometric argument, and you saw that the double branch cover was just like a 1 handle and a 2 handle. It was really a major manifold. So here, yes, it is constructive in the sense we know what the rational ball is, but we may not know exactly what it looks like. It could be pretty complicated. All right. So this brings up the next definition. And this is what chi-slice means. So if I have a link and it's called chi-slice, what I mean is that it bounds a properly embedded surface in the 4-ball, no closed components, and that surface has Euler characteristic 1. This definition is also due to Donald and Owens. It's in the same paper. So in that paper, they introduced this notion and they talk about concordance and they prove this thing. So there's a lot in that paper. The only aspect of it I'm really looking at though is this theorem. And so with this definition, I can reformulate the last theorem in a much simpler way. So if L is a chi-slice link and the determinant is non-zero, then the double branch cover bounds a rational ball. And so this is very similar to the first statement I wrote, where up above, the first thing I told you about knots is if you have a knot, then the double branch and a slice, then the double branch cover bounds a rational ball. Now I'm saying if I have a link that's chi-slice, then the double branch cover bounds a rational ball. So you can think of this as a generalization of slice knots. These are different than slice, like sort of classical slice links. A classic slice link is you have a link and the components bound disks. This is a little different, but I like this notion because of this fact, again, that you take the double branch cover and you bound a rational ball. It's a good way to construct these rational balls. All right, so a couple of notes to make about this. The first one is that this is a generalization of sliceness, like I said. If L has one component, then sliceness is the same thing as chi-sliceness. So if you have one component, you're just a knot. The only surface with Euler characteristic 1 with one boundary component is the disk. So chi-slice is the same thing as slice. Now let's do a little bit more history. There are a lot of examples of chi-slice links that came out way before this definition was proposed and then written down. So the first set of examples goes back to Katz and Harrer again, back to the 70s. It's I can't write while I talk, so I just combine all my words. And what they showed is that they produced a lot of Montesinos links that are chi-slice. So they had a lot of examples of chi-slice Montesinos links. And the double branch covers of these things were Brief-Form spheres that bounded rational balls. Montesinos links. If we fast forward to Liska, about 15 years ago, he gave a classification, a full classification of chi-slice two-bridge links. Even though he wasn't, using this terminology or necessarily even thinking about this aspect, this came out of this paper where he classified lens spaces that bound rational homology four balls, and this is sort of equivalent to that classification. It's all written down in his paper really nicely. Really, he was after lens spaces that bound rational homology four balls. And the reason why these are equivalent is because lens spaces are the double branch covers of two bridge links. Take any two bridge link, take the double branch cover, you get a lens space. And so in classifying this, he ended up classifying this. And so I'll say a couple of words about how this classification works. And there are essentially two steps. The first step is you have to show something as chi-slice, you have to do something pretty explicit. You actually have to construct the surface that you're looking at. You have to find an Euler characteristic one surface. So the two steps are, first need to construct Euler characteristic one surfaces. And the trick is just to use band, or also known as ribbon moves. And that could be a way to construct. So I'm going to say this a few words about this in a minute to talk about what these pictures look like. But it is just pictures. You have some sort of link and you want to attach some bands. And this is where it's going to look a lot like what Maggie was talking about. And you want to attach bands in a certain way so that you end up with a collection of unknowns. You just get a known link. So I'll talk about that a little bit in a second. So he exhibited all of these moves to show all of the two bridge links that he was proposing were chi-slice, were actually chi-slice. And then to obstruct the rest from being chi-slice, he obstructed by showing that the double branch covers over these links, all the others, do not bound rational balls. And again, this comes down to this, he's really looking at lens spaces that bound rational balls. And this obstruction, this is where the bulk of the technical work comes in. This applies Donaldson's diagonalization theorem and the existence of lattice embeddings and things like that. Now I'm going to say very little about this. I could spend if this is a 2-hour talk, I'd be able to get pretty deep into this side of the story. But I'm probably not going to say much more than just, give a name drop. And, if you know this story, great. If you don't, the very little I would add on to this probably would be meaningless if I said anything more. So I'll just leave it at that. But I do want to say something about band moves. And this is just in case, this is something that maybe all of you already know about and know how to do these moves. But if you've never thought about it before, I want to make sure it makes sense to you. So the idea of using band moves or ribbon moves to prove something is chi-slice, meaning it bounds an Euler characteristic one surface. This will only work if the surface is a ribbon surface. So that's sort of a key. If F is ribbon. Because what I'm going to do, I'm going to take a collection of disks and I'm going to attach one handles to it, and there'll be no maxima. So these are all going to be ribbon surfaces. And so just to think about it, what does it mean to have Euler characteristic one? Well, to calculate the Euler characteristic of a surface, you look at the number of index 0 critical points or number of 0 handles, or if you're doing a CW complex, the number of 0 cells, subtract off the number of 1 handles, and you add the number of 2 handles. There's your Euler characteristic. Now I have a ribbon surface, so I have no two handles. I have no index to critical points, no maxima. So this tells me the difference between the 0 handles and the 1 handles has to be 1. In other words, number of 0 handles, 0 handles equals number of 1 handles plus 1. All right, so that's not a hard computation. But however I build this surface, the number of 1 handles has to be 1 less than the number of 0 handles to ensure that it's an Euler characteristic 1 surface. And so let's just do one. Let's do like a schematic thing, or not even schematic, actually a concrete example. Let me take 3 0 handles. Here they are. 3 disks, in other words. So this is where this picture is going to look a lot like Maggie's. And I'm going to attach 2 1 handles. And so when I do this, the Euler characteristic will be 1. And I'm going to attach these handles, and these are bands. So really, maybe I should be talking about these as bands, since that's the language we've been using today. I'm going to attach the band so they go from one disk to another disk, or maybe it goes from a disk to itself. I didn't mention this before, but I put no restrictions on these surfaces. They don't have to be connected. They don't have to be orientable. And in fact, most of them, they're going to have non-oriented components. They're going to be a lot of Mobius bands and annuli and different components in these surfaces. And so we'll see that here. So let me attach some bands. Here's I don't know, let me do this. And I'm going to do something kind of bad. This is a picture in S3. So this picture, it can intersect itself, this surface. But when I push it into the 4-ball, I want to make sure that I'm able to push it in the 4-ball and make all the intersections go away. So the picture I'm going to have is going to have these ribbon singularity things. So I'll sort of say more about this in a bit. Let's say it goes through there, maybe it comes out through there, and then, I don't know, goes back to where it came. So I have this band. And let me do one more band. Let me go from this component to this component. Maybe I'll put a twist in there. Okay, so here's an Euler characteristic 1 surface. As it's drawn, like I said, this is immersed in S3 because I have these lines of intersections here. But if I push this into the 4-ball, the surface, you could think about, all you have to do is, if I take this disk, this original disk, and push that a little bit into the 4-ball and leave this band right where it is, the surface no longer intersects itself. It's kind of one of the pictures that Maggie drew too is kind of similar to this. So I can just push this disk and this disk into the 4-ball, and now I have a surface that's embedded in the 4-ball. And the boundary is whatever length this is. So this is actually an Euler characteristic 1 surface, and I can embed it in the 4-ball. And the boundary is this link. So let me just draw the link and forget about the surface, because now we want to go backwards. How did I do this? Like that. Goes through there. Goes this way. Okay, there's my link. So this is a 2-component link. Now it's drawn in a very suggestive way. You can still see the disks and the bands, but typically in this story, you're just starting with a link and you want to decide if it bounds an Euler characteristic 1 surface. And so now I want to think about, how do I go backwards? Like, I obviously know this bounds an Euler characteristic 1 surface because I constructed it that way. But how do I go backwards to actually see that surface, or to prove that this does bound a surface if I didn't start with that surface? And the idea is just to undo the bands that I made. I want to undo these 1 handles so that I could count them. So what I can do is I can use band moves to undo the 1 handles. And so the way a band move works is I'm just going to attach essentially like a little band, again, it could go from 1 link component to itself, or it could go between 2 different link components. It doesn't really matter. And I could do 2 of them. And what I mean by a band move is I'm going to just cut this thing. So I have that band that I attached, and I just want to cut along that band. You can think of it that way. And when I cut along those bands, that corresponds to essentially getting rid of those one handles, because now I can isotope this down, and I can isotope this other portion around, and I can isotope this band down, and I just recover my original unlink. And this obviously bounds those three disks. So what I see here is that this link bounds the surface. It starts with three disks, and then I have two one handles that I can attach to recover my non. So it's just doing this process backwards. So in general, if n band moves yields n plus one component unlink, then the link bounds an Euler characteristic on surface. And again, it was crucial here that, I have to, if I do n band moves, I need an n plus one component unlink. And that's because, again, if I want this to be an Euler characteristic one surface, then the number of zero handles and the number of one handles have to differ by one. That's why I have that. So this is the thing that you can use to show something is chi-slice. You can play this game. But now, of course, the link that you're given could be much more complicated than this. The way I drew this, I drew it from this Euler characteristic one surface, so we knew how to cut the one handles already. But more generally, it could be much harder to do. And it's just, if you don't really have anything to go on, you just start with a link diagram, and you just start like adding bands and then cut and then just isotope and see what you get if you're going to do it very naively. But a lot of times that's how it starts.
Jonathan, I have another question. So how often does this happen where you perform n band moves and you get n plus one, an n plus one component unlink? Like, is it possible that you could perform n band moves and get like something like much less, like the number of components is, I don't have a good feel for.
Yeah, like you could do, for example, if I do, let's do the trefoil. Let's just do a one component link. If I do the trefoil, I could do a single band move, which is just this, and I get an unknot. And so that tells me that I bound a torus essentially, because I had a, that tells me I bound a Mobius band because I just had a disk and I attached this thing to it, this one handle. So yeah, that can happen. Like, it doesn't have to be n plus one, it could be less, but it can't be too much. I guess there are sort of, there can't be that big of a difference, I suppose, just because the number of components that you're starting with. But I don't know if that's a satisfactory answer. So, but here's an example where it's not n plus one, it's just n. All right. Okay, so this is what we use to show something is chi-slice. Now, really what this shows is it's sliced, but also the surface is ribbon, which is a pretty specific thing. Oh, okay. Good, Vitaly, my collaborators, fact-checking me. Yeah, so a band move can increase the number of components. It could also, maybe Vitaly, what you meant to say is it increases the number of components by one or keeps it the same. Yeah, okay. Cool. All right, so let's move on to three braids finally. This is the question that Vitaly and I are currently thinking about. This is a work in progress, so I'm going to tell you the things that we figured out. and tell you things that we don't know yet, tell you about some mysterious cases, and what we hope to see, I suppose. So which three braid lengths are chi-slice? Now let me remind you about how three braids look, just a little bit of review. So to start with, if I have a three braid in general, I can, what does that even mean? I just take three strands and I just put a bunch of crossings into it. And I can do a bunch of random stuff. Maybe I do this, and then maybe I do that, and maybe I do that. And so I end up with this three braid with a bunch of crossings. But now if I want to turn it into a link, I just have to take the closure and close the thing up. So the three braid link is this. Okay. And now we can algebraically encode this three braid by looking at these generators of the braid group. So sigma 1, I'm going to refer to it as taking this crossing of the first two strands. Sigma 2 means do this crossing on the second two strands. Now, if I take any three braid, I can write it as just a word in these generators, essentially. So if I look at this, the first thing I see is sigma 1, then I see sigma 1 again. So I have a sigma 1 squared, and then I see sigma 2. But the crossing is wrong here, so I'm going to make that a -1. And this is another sigma 1. So I can, for any three braid, I can write down a representation using these symbols. And one in particular is if I do sigma 1, sigma 2 cubed, this gives me a full twist of the three braid. So here it is, it's just a full twist. So now there's this result of Marisugi that tells us what all three braids look like. And it turns out if you take any three braid, anything that looks like this, you can essentially isotope it. So it has one of these types of representations. And so here, D could be anything. So H is this full twist you could put in the three braid, and D could be any integer in all three cases. So you can put a whole bunch of positive or negative twists in the three braids. And in this case, there are some restrictions on what M can be. And this last case is kind of the generic case. This is the one where the most complicated stuff happens. This is where like most of the three braids live. And so I have A1, A2, AN, these exponents. And the restriction that I have on these A's is I want them to all be greater than or equal to 0. And one of them has to be strictly greater than 0, at least one of them. So you can represent any three braid in this way. And so this is the way I'm going to be thinking about three braids. I'm going to be thinking about these three different cases and thinking about chi-sliceness. And I further want to restrict this list to a simpler list. I actually want to think about quasi-alternating three braids. Now, I'm not going to define quasi-alternating because it doesn't really add anything to the discussion necessarily. All you really need to know is which of these are quasi-alternating, because those are the ones I'm going to focus on the most. And there's a theorem of Baldwin that tells us exactly which ones are quasi-alternating. So if you're in type A, then you're quasi-alternating if and only if D is plus or minus 1, and M is either 1, 2, or 3, or -1, 2, or 3. And also, it's not that important, but the signs have to be different. So if D is plus 1, then M is going to be negative. If D is -1, M is positive. If you're of type B, then you're quasi-alternating if and only if D here is 0 or 1, meaning you have no full twists or a single full twist in your three braid, and there's no restriction on M. And you're of type C, then you're quasi-alternating if and only if D is 0, 1, or -1, and no restriction on the A's other than what's already here. So these are the ones I want to focus on. And the first two cases are super simple to prove. What's quasi-alternating in here and what's not, or sorry, not quasi-alternating, what's chi-slice in here and what's not. And so I'm going to do them for you. And I'm going to label them as observations because that's really what they are. It's nothing deeper than that. But I want to show it to you. So the first observation is if I take any quasi-alternating three braid in the first type. Yep.
Sorry. So just to be clear before you move on, you're focusing on quasi-alternating three braids because you know they bound ribbon surfaces?
Oh, no. So I don't know that yet. So what I want to do is I want to classify which of these are chi-slice. And really, the reason why I'm focusing on quasi-alternating will be maybe more clear at the end. It just turns out that if it's not quasi-alternating, then D in this case can be really big or really small, really negative, and the invariants we use to obstruct them from being chi-slice kind of don't really give us any new information or anything useful. So that's why I'm focusing on quasi-alternating.
But what about three braids? Why three braids?
I think for three braids, I was working on a project last year, and there's this paper up where I classified torus bundles over the circle that bound rational homology circles. And part of that classification boiled down to classifying certain rational homology three spheres that bound rational homology four balls. And those rational homology three spheres happen to be double branch covers over three braids. So a lot of the technical work in here was sort of already done in this previous paper that I did. And this is before I knew anything about chi-sliceness. And so it just kind of, you can think of it as almost like a natural extension of that paper, even though it's coming at it from two completely different angles. That's why, that's why I started thinking about three braids.
Oh, sorry, can I ask another question? So how many components to these three braid links? Like either 3 or 4, or can you have an arbitrary number? No.
Well, it'll
no,
be 1, 2, or 3.
1, 2, or 3. Right. Okay.
Yeah.
Thanks.
All right. Okay, cool. So chi-sliceness of quasi-alternating three braids. Focusing on this first case first, observation, they're all chi-slice. And I'm going to prove it to you really quickly, I guess modulo some details. The first part is if you draw these three braids with this information, with these representations, you'll see that it's either this two-component link or this three-component link. So these are either that, or it could be their mirrors. But if you take the mirror of something that bounds some kind of surface, the mirror will bound the same kind of surface. So that doesn't really do anything. And so you can show that these are either that two-component link or that three-component link. And I can exhibit that these are chi-slice just by doing quick band moves. And so in this first case, I can attach a band from the blue component to itself. So I'm going to, let's see, let me do this right. I'm going to put a little twist like that. And so if I take this and do this band move, now let me draw the blue. There's no point in having so many colors. So I do this band move. Then you can see you can just isotope this, and these things come apart. This is just a two-component unlink. So I did a single band move. I got a two-component unlink. So this bounds a Euler characteristic one surface. It's also a ribbon surface because I found this using band moves. Whenever you use band moves, the surface is necessarily a ribbon. And in the second case, I could do another band move. I'm just going to do this one. I'm just going to merge those two blue unknots. And so when I do that, I get this, which of course is just two unknots. So a single band move gives me the unlink that also bounds an Euler characteristic one surface. And that's using band moves. But looking at these, you can see the surface anyway. There was, I didn't really have to go through this work, although I wanted to just to exhibit the band moves. But you can see the Euler characteristic surface in this picture. It's just the spanning disk of this black unknot and the annulus going between these two components. Now, again, this is an immersed surface in S3, but if I push this into the four ball, this does become an embedded surface in the four ball, and it has Euler characteristic one. So you can see the surface right there. There was not really a point in doing the band move. And you can see the same thing for this other one. I can isotope this picture and make it look like this. Maybe my crossing might be wrong. I don't know if that's the correct crossing, but you get the idea. And I can see the same thing. I have my spanning disk of the black gun knot, and then I have a Mobius band as my other surface. That has Euler characteristic 1. Sure, I have this singularity, but pushed into the 4 ball becomes an embedded surface. And so this has Euler characteristic 1. Okay. So that's these quasi-alternating of type 3 or type A. They're all chi-slice, super simple. It's just an observation. Now, for the second case, type B, D can be either 0 or 1. Just to remind you, it doesn't matter that much, but they look like this. So D could be 0 or 1. M is either -1, -2, or -3. So there are only 6 cases to consider. And this is even simpler because, all right, the statement is it's quasi-alternating 3-braid of type B is chi-slice if and only if D is 0, M is -1, or D is 1 and, oh, that should be an M. M is -3. And this is really easy to see because these are unknowns. So no work required. Of course, it bounds a disk, but it bounds Euler characteristic 1 surface. Now, to obstruct the rest from being chi-slice, the others are either the trefoil or the hop flank. And obviously the trefoil is not slice, so not chi-slice. Now the hop flank is a 2-component link. This is also not chi-slice. One way you can do it is if you look at the double branch cover, and there are a lot of different things you could say about it. If you look at the double branch cover of this, double branch cover of S3 branched over the hop flank, you're going to get the lens space L21. And this does not bound a rational ball. Doesn't bound rational ball. And of course, if you're chi-slice, the double branch cover has to bound a rational ball. And this doesn't bound a rational ball for various reasons. I mean, you can use Liska's work. He tells you it doesn't, but it's simpler than that. For example, the first homology of this is E mod 2. But to bound a rational ball, the first homology has to have order a square. So you can use that. So that's the second observation. All right. So those are the first 2 cases. They're pretty simple. The third case is the hard one. This is where all the work has really gone into, and we've sort of been doing a lot with it. So the third case, and this is sort of the generic case. Most 3-braids fall under this kind of category. And we are quasi-alternating if D is 0, 1, or -1. So those are the cases I'm going to focus on. And this is not going to be an observation. This I'm going to upgrade to a theorem. And there's a lot of stuff in here. So let me maybe just show this first. So L is going to be a 3-braid link of type C. And this is the representation. Just to remind you, all of these A's, all of these exponents are integers. They're non-negative. One of them has to be strictly positive. And what I'm going to say about this theorem is this is the takeaway. This is a almost classification of chi-slice quasi-alternating 3-braids of type C. So that's what this is getting at. In the first 2 cases, I was able to say exactly what happens concretely pretty easily. Here, we get pretty close, but there's some interesting stuff that happens that we're still thinking about. So like I said, this is a work in progress, and so I'll indicate where the progress is. And I should also say that this theorem is kind of a culmination of work that Vitaly and I have been doing. I mean, first we were doing it independently, and then we more recently came together. So a lot of things in this big theorem are due to Vitaly, some are due to me, some are due to both of us more recently. So as I go through, I'll try to indicate, who did what independently. because we both released papers last year that sort of said some things about this story. And, you know, I probably wouldn't be that careful, but he's in the audience, so I feel like I should probably be a little careful about it. All right, so here's the theorem. I have all of these sets. What I'm going to say for now is forget, don't look at this. It's disgusting, and there's so much just stuff in there. It's, you know, I don't want you to focus on that. I will erase that in a bit and sort of look at those. But for now, don't look at them. All you have to know is that these are sets of strings of integers. That's what all of these things are. And these sets are pretty much going to refer to the exponents in this representation. And so here's the first part. So if D is 0, these are alternating. Oops. These are actually just regular old alternating links. And if D is 1 or -1, then it's no longer alternating and it's quasi-alternating. And so this first case is something that Vitaly was looking at. And he put out a paper on arXiv, I don't know, November, December, where he talked about this case. And the statement is, if D is 0 and this string of integers, so these are the exponents in my representation, if these exponents do not belong to this set, that's sort of the first condition. So I just want it to not belong to this set. Then I have like then there's a full classification. Then we could say L is chi-slice if and only if that string belongs to one of these others. Oops. S2A, S2B, S2D, S2E. So modulo this set, this S2C, this is a classification of chi-slice, alternating chi-slice 3 braids with D equals 0. And so there's this issue with this S2C, you know, it's we're assuming it's not in there because weird things happen in there. What the theorem is saying is if you're outside of any of these sets, then you're not chi-slice. And if you're inside any of these 4 sets, you are chi-slice. That's what the theorem is saying. But if you're inside S2C, then you may or may not be chi-slice. And in fact, there are examples that are chi-slice and there are examples that are not chi-slice. So S2C is super mysterious and it's something that we're still exploring. This is sort of the part of the work in progress portion of this. And this is also the almost classification portion of this, where, you know, we haven't been able to pin down what happens in S2C. So what I want to do is I just want to highlight the proof of this. And it's in 2 parts. The first part is if you take anything in these sets, then you're able to do some band moves and show that 3 braid bounds an Euler characteristic 1 surface. And then the second step is to show that if you're not in any of these sets, and, you know, still not in S2C, then the double branch cover does not bound a rational ball, obstructing them from being chi-slice. So it's a 2-step process, just like Lisp is. And so I'm going to skip over these other 2 for now and go down to that proof and sort of, you know, show you some beautiful pictures that Vitaly put in his paper. And so I'm going to start with D equals 0. We have this representation. Since D is 0, I have no H here. And I'm assuming that these exponents are not in that set S2C. And so what Vitaly showed is that if you're in one of those other 4 sets, you can do band moves to show that it's chi-slice. And so here's one version. This is if you're in S2A. Here are the band moves. So here is the 3 braid. And before moving on, I want to tell you what these little boxes are. So these boxes, I have this green box and this blue box. I have to go back up to what these sets are. And I'm going to erase all the scribbling I did and show you some things under the hood here. So let me get some green. So if you notice in a lot of these strings, I have this B1 to BK and the CL to C1, and this pops up a lot in pretty much most of the strings. And in particular in the S2A case, this is the one I'm looking at, I also have it. So these strings of integers, they're sort of dual in some sense. And I'm not going to get into what dual means because you can ask me later, I guess, if you want, but it's not super important. But because these are dual, some nice things happen when you do band moves. And in particular, you're able to sort of cancel things out nicely. And so that's sort of the thing I want to highlight in these strings. You can ignore everything else. Just notice that in most of these strings, you have these kind of dual red and blue substrings. And so that's what these boxes are referring to. So this is just referring to all the crossings that you get when you look at those dual strings. And so this is what we do. We do this band move right here. So Vitaly attached this band with a little crossing, isotoped, and it becomes in this position. And now comes the fact that these are dual, these boxes. And if I sort of look at them in this direction, I'm able to do a lot of isotoping to just cancel all of the complexity in these two out. And I just end up with this diagram. So these two just essentially cancel each other out. It takes a lot of isotoping stuff, but it works out. And this is just a 2-component unlink. So one band move, one handle, and I have 2 0 handles. There's my Euler characteristic one surface. So much more complicated than any of the pictures I've drawn up until this point. But the key again was that I had those two dual substrings up here. And this is sort of the key in all of the cases, most of the cases at least. Most cases have these. And to produce these Euler characteristic one surfaces in all of these cases, it uses that duality. Okay, so that's the one direction of it. That everything in here is chi-slice. The reverse direction is showing that everything outside of here is not chi-slice. And this goes back to my work from last year, where I showed that if you take the double cover of S3 branched over one of these links, then it bounds a rational ball if and only if the string is in one of these. Okay, I didn't say what S2 is. S2 is going to be the union of all of these, like S2A, 2B, 2C, 2D, 2E. So this bounds a rational ball if and only if these exponents belong to that set. And the way I do it to prove that they bound rational balls, I just construct them using Kirby calculus to obstruct the rest from bounding rational balls, use Donaldson diagonalization and lattice analysis to get through that. So now what this says, so this proves it. This proves part 1 now. So we've shown it. If you're not an S2C and you're in here, you're a chi-slice. If you're not in here, you're not chi-slice. But there's a little bit more information that this gives. It tells me that if I am in S2C, the double branch cover still bounds a rational ball. And so that means that, if I'm in S2C, still bounds a rational ball. So all the links in here are unobstructed from being chi-slice just by looking at Donaldson and lattice embeddings. And so this is mysterious. You might think, all right, well, it's unobstructed. All the double branch covers bound rational balls. Perhaps they are all chi-slice. Well, that's not the case. It turns out there are examples of links in that family, and all of them are actually not, that are not chi-slice. And these are due to Satori and more recently this Seto, Meyer, 2 of the Millers. I think one of them is here, Park and Stipschitz. And they produce, I think, maybe like 4 or 5 knots that are inside of this family that are not chi-slice. I mean, they're not slice. And they were obstructed using twisted Alexander polynomials in this latter paper. And so not everything in here is chi-slice, you can say. So then you think, all right, well, maybe they're not all chi-slice. Maybe it's that simple, but no, it's not that simple. There are infinite families of chi-slice links in there. And so Vitaly wrote down an explicit family in his paper from last year, and I sort of came up with more families. So there are plenty of examples of chi-slice things in there. There are examples of non-chi-slice things in there. So this S2C family is really interesting. And these links also, I should mention, they're negative amphichiral, if that means anything to you or interest you. Okay, so that's the whole story with the alternating case with, case 1 if D is 0. we have almost a classification. If I move to the other cases where D is 1 or -1, then we do have a full classification. And really these, the strings here, I was pretty explicit about where these strings lived. They had to be in S2, A, B, D, or E. In this case, they live in the first 5, but also they could have these like dual strings and they could also live in the first 5. So instead of saying a ton of words and use a ton of notation, I'm just saying we classified them in both of these cases. And this is, the proof of this is a lot like the proof similar to the first case, except with the lattice analysis in Donaldson, we actually had to go in and, not everything that we wanted to be obstructed was obstructed using Donaldson diagonalization theorem and lattice analysis. So we had to use, we also had to use techniques of Ibuka and Green, which combines Donaldson and D invariance to obstruct sort of some cases that were unobstructable by what we had done in the past. But more or less, these are done. And like I said, this is a work in progress. So I'm going to say it's still in progress, the details that, this is all lattice stuff. And so it can get kind of tedious. And there are a lot of details, which we're still working out. I think we're pretty confident that, we know what's going on. We have enough computations to feel extremely confident, and most of the cases are handled. But I should put that disclaimer in there that, maybe we release a paper at some point and, this is no longer true, and just so you know. Okay. So kind of out of time. Maybe the last thing, oh, sure.
Sorry, I forgot. Can you say again what D represents?
D is the number of full twists that you put in the 3 braid.
I see.
So it's just the exponent of this guy. Yeah. So you have all this.
Can I see a picture? Can I see the 3 braid length picture again?
Yeah, sure. Let me go back up to here. So when I have H, I just have this full twist. It's sigma 1, sigma 2 cubed.
Yeah.
So
Okay. Okay. I see. Okay. Great. Okay. That's what you mean. Okay. Great. I see.
Cool. So maybe the last thing I will say, though, especially since you were asking BG about, we were thinking about quasi-alternating, but you can say a lot in the non-quasi-alternating case. So, if D is not 0, 1, or -1, if D is bigger than that, there's still some things we can get, but it gets a little bit more complicated and you probably need some more subtle obstructions. So I'll just say like a quick word about this. If we are not quasi-alternating, so let's just look general 3 braids. They're one of these 3 forms. I wrote this down earlier. What I could say here is that in the first case, these are all chi-slice. And it's pretty easy, again, just to find ribbons and show it. In this case, we have chi-slice if and only if D is, I forgot what they are. It's the ones that I showed you that were just unknots. I think I have, oh, here it is. D is 0, M is -1, D is 1, M is -3. And so these happen to be unknots. The rest can be obstructed by simple things like if M is -1 or -3, this is just a knot, and none of them are sliced because their signatures are non-zero. You can sort of see that. If it's 2, then it's a 2-component link, and you can look at the double branch cover and see that that's not, can't bound a rational ball. So it's kind of simple. These are pretty simple 3 braids to work with. This is the hard case again. This is the generic case. If it's not quasi-alternating, that means I'm talking about D is greater than 1 or D is less than 1. So I have a lot of twists in the braid. And what I can say is if D is even, and if my string, if the exponents are not in that set S2, then not chi-slice. And it's obstructed just from Donaldson, essentially. And if D is odd, and this string is not in S1, then again, it's not chi-slice. I can say that. And the reason why I'm allowed to say this is because when D is even, the lattice embeddings you get from Donaldson, they're all the same. So adding twists into it does not affect the Donaldson obstruction. It's all the same. And same if D is odd. If you add an odd number of twists, you're always going to get the same answer. All the lattice embeddings will look the same. And so you're able to obstruct all the same things when D is either even or odd. But if you're in this set, the issue is the Donaldson obstruction no longer helps you because it did not obstruct anything in here when D was 0 or 1. So it's not going to obstruct anything in here for other values of D. And so, I feel like the links, when D is bigger, those links are probably not chi-slice. But to really obstruct them from being chi-slice, we need an invariant that would take into account this kind of twisting of the three braids. And so, but that's something that's maybe more in the future. It's not something I've thought too much about. If D is not 0, 1, or -1, we focused on this quasi-alternating stuff, but that's maybe something for the future. So I'll stop there. That's what we've done, and thanks for listening.
Okay, let's thank John for this great talk. Thank you very much.